today, the two problems that I gave, they both have sources. And so level 3 source is the 2015 HMMP, and the level 4 source is the 2010 JMO. And so for today, I'm going to first start with the level 4 JUMO problem, the level 4 problem, the 2010 JUMO. For this problem. So the statement was, pull it up right now. Okay, so the statement was that define the set of the numbers AK, where K is from 1 to n, and it's the key number of a permutation of the numbers from 1 through n. And so then we define P of n to be the number of permutations of the first n positive integers such that K times AK is a perfect square. Yeah. And then so we want to find the smallest n such that 2010 divides P of n. Okay. So that's the problem. And so first of all, so the basic logic behind this solution is just that for all k, you have to have that AK equals k times m squared for some integral m. Yeah. And so, and a way we can prove this is basically that we can split this into cases. And so first of all, clearly you can see that if AK equals k for k in the range of 1 to n, then this permutation is clearly one that works. And so after this, what you can find is that yeah, sorry about that. And so the way this works is basically, one way to do this is basically to set the set S to be the perfect squares. So 1 squared, 2 squared, 3 squared, so on. And so basically, this necessarily must k. And so first of all, if this is true, then it's all of the k times ak are in the form k times m squared, or mk squared. And these are clearly squares. And so in here, oh, and also for this, yeah. And then so if this is not true, then k would have to be a multiple of a perfect square. I forgot to mention that. And so if k is not a multiple of a perfect square, or basically if k is square free, then in this case it would have to be true that ak times k is a perfect square for some integer m. And if k is square free, then it's also true that ak times k, if k is not some perfect square multiple of k, then you can just look at the prime factorizations of these numbers. And then, yeah, we can just from that see that it's impossible. And now if k is a multiple of a perfect square, then let ak equal pk times mk squared k and pk are both integers. And this is one way of writing that. And so from here, since pk is square free, then we can express sorry, it's not ak, it's just a is in the form of this. Sorry, not k is in the form of this, sorry. And so then in this case, then ak would equal pk times n squared for some integer n. And so once again, you can basically see that it's almost a repeat of the ak of k being square free case, except now there's another square factor in, but this doesn't affect it by anything really. And so now you can see that ak in this form. Okay, so if k is in this form, then we see that ak equals pk times n squared, and this holds for all k, and n is some integer. So I'm gonna scroll down a bit. ak equals pk times n squared. Okay, so then we can split the numbers from 1 to n into a couple of different sets. And these sets are for the distinct pk. And so, yeah. And so now we want 2010 to divide p of n. And so we have that 2010 is equal to 2 times 3 times 5 times 67. Yeah. And so the number of ways to split 1 to n into distinct pk is just the product of the corresponding n's for all pk. The maximum corresponding values of n for all pk. Okay. That might be done a bit poorly, but yeah, and that works. So 2, 3, and 5, we can see are all easily done because 2 factorial, 3 factorial, and 5 factorial are all a lot smaller than 67 factorial. And so what we really need to care about is just the 6th factor of 67. And so there needs to be a set of there needs to be a set of 67 multiples of a number that are all perfect squares. And so the way this works is just clearly the minimal value is when pk equals 1. And in this case, the maximum value of n would be 67 squared, which is equal to 4,489. And if you really want to check this, you can eventually confirm by hand that 2, 3, 5 all satisfy are all also factors. And it's not really hard to do this because there's a bunch of multiples of 2, 3, and 5. So yeah, does anyone have any questions about how this problem was done? It is now going to be on the other one, the level 3 one. And so in this case, Calvin has a bag of 50 reds, 50 blues, and 30 yellows. And so he pulls out 65 balls at random, and he pulls out 5 more. Actually, better. R equals B plus 5. And so we want to find the chance that the next ball he pulls out, which is the 66th ball, is red. And so one way you can do this is just to basically look at the expected number of reds that are left. And so the way this works is just that the chance that the next ball is red is just the expected value of the number of red left divided by 65, because there's still 65 balls left. Okay. Yeah. And so now to actually calculate the expected number of reds that are left, we can first make a bijection. And so the way that this bijection works is just that we can take the set of 65 balls that have been taken out. Sets of taken out balls. And so then we can flip the blues to become red and the reds to become blues. And then after this, we can look at the set that was not taken out, that was left behind. And then now we can treat this as the taken out set. And so in this way, there's a bijection, and there's no way that this bijection sends one set to itself, because the only way this can happen is if there's 25 reds, 25 blues, and 15 yellows, sorry. And while this does add up to 65, it does not satisfy the condition that there are 5 more reds pulled out than blues. So we can effectively ignore this. And so what this tells us is that the average, and so this tells us that this gives a bijection for Y yellow balls, and it turns it into 30 minus Y yellow balls. And so this is good because by the linearity of expected value, the expected value of the number of yellows is just 30 over 2, or 15. And that's really nice. And so now we can basically treat the expected value of the values of R and B as any real numbers, because now we're just basically replacing these values with their expected values. So the expected value of yellows is 15, and so 30, and the reason, and another thing is that another reason that treating the taken out set and the left set as nearly the same is because there's a total of 65 balls that have been taken out, and there was initially a total of 130, and 65 times 2 is 130. And so that's basically the whole reason the bijection works. And so on average, the expected value of yellows is 15. And so what that also means is that the expected value of the blues plus the reds is equal to 65 minus the expected number of yellows. And so the expected number of yellows was 15, so it's 65 minus 15, or 50. And so now we have that R equals B plus 5, and so we can just directly solve these equations. And so the expected value of reds taken is 27.5, and expected value of blue taken is 22.5. And so we want the expected value of the red last. And so that's 50 minus 27.5. Yeah. And this is 22.5. So this is just equal to 22.5 divided by 65, and we can multiply this by 2, so it would be 45 over 130. And now we can divide this by 5, and that simplifies to 9 over 26. Hold on a second. Okay, sorry about that. And so that tells us that the chance that Calvin's next mall is red is just 9 over 26. So does anyone have any questions about this problem? And if not, that is basically it for today's training.
Okay, thanks.
Okay, well, goodbye then, and thank you for coming.